All right, Jennifer, thank you. It is 7:25. Time for part two of our Wise Guy segment this morning. Matt Sellen rejoins us talking about magnets.
Oh, yeah. So what we, just a recap from the first part, all atoms can behave like little magnets. And if you bring a big magnet up to some material, it can either be weakly attracted, that's paramagnetism, or weakly repelled, that's dimagnetism. And if all the little magnets in the material tend to line up in big groups, that's ferromagnetism. That's when you can make big magnets like that, because you can actually make them remember their orientation.
Okay.
But anyways, if you run an electric current through a magnet, you get a force. And I just wanted to do that first here. So here's a wire. We're just going to hold it inside the poles of this magnet. I'm just going to attach it to the battery, and you see it jumping. It's not jumping because we're moving our fingers. It's really just jumping because I'm running a current through it. And that points out this very intimate relationship between electricity and magnetism. Okay, and we know that's true because you can actually use magnets and wires to generate electricity. That's how a generator works in your car and at the Clinton power station and so on. And so I want to show you something that's kind of neat. If you take this little magnet right here and you run it back and forth across this piece of copper, and copper is not a magnetic material. It doesn't stick. It still is kind of hard to move.
There's some force there.
And the reason is that when you move a magnet near a conductor, you induce a current. And the beautiful and interesting thing is that the current that's induced in the conductor, in this case the copper, makes a magnet of its own, which opposes the magnet that you are moving. It wants to keep it from moving. So you see this thing actually, you know, if I drop it over here, it drops like a piece of metal. If I drop it here, it goes down kind of slowly. It's kind of interesting. And the better the conductor is, the more this effect is noticeable. So here I have, of course, is my excuse to bring in liquid nitrogen.
Oh, it's always a good idea.
If you get a piece of copper and you get it really cold, it becomes a much better conductor. So the resistance of the material goes down if you make it really cold. And now if you actually...
there's a lot more force there.
So if you just let this thing slide down there, just let it go. Okay, it's not sticking to it.
No.
It's really just sliding ever so slowly. It's not because it's attracted magnetically. It's because as the thing moves, it induces currents which oppose that motion. And if you actually see it,
it's like a slinky.
Yeah. So I'll kind of do it sideways, and you can. Whoops.
We're singing the Slinky song.
Go ahead. You sing. You first.
You want to go? You want to sing with me?
Yeah. No, I don't know the words.
Don's singing right now. Walks downstairs alone or in pairs. It makes a slinky sound. The thing. That's enough singing for me.
Right. And so if you actually moving this thing now is hard. If you go ahead and just shove it back and forth, you're doing a lot of work.
Yeah.
Okay. Now that is energy that you are creating. So you're making large currents flow in this piece of copper. And basically, if you had built this thing differently, if this was a bunch of wires and those wires went someplace, you'd be generating electricity right now.
Oh, cool.
Okay. So that's how electric generators work. Awesome. So I just think that's kind of neat.
That is very cool.
Yep.
And very cold.
It's very cold. Right. Yikes. Okay. Sorry. I didn't mean to spill that on your.
That's all right. I like the stuff anyway.
Yeah. So, anyways, that's how electric generators work.
Thank you, Matt.
Sure.
Very good. We'll see you in 2 weeks.
Yep.
All right.